In this video, I'd like to compare and contrast how we might use proportions and dimensional analysis to find and to convert units. The example that I'm going to use to illustrate here on this first page is I'm going to convert 2.36 grams into its equivalent amount of micrograms. So very briefly, I just want to summarize what I've written up here, comparing the use of proportions and dimensional analysis. I get comments from students who tend to prefer proportions for some examples and use dimensional analysis in other examples. And to be honest, I find myself in that camp as well. But I also see that many students tend to get confused and don't understand really that you can choose to use one or the other. It doesn't matter depending on the context of the problem. You could use dimensional analysis, but you could also use proportions, and that the mathematics behind it is very similar in the sense that as long as you implement these procedures, either one correctly, you're going to arrive at the correct solution. So you don't have to think, oh wow, I need to use dimensional analysis because using proportions isn't going to provide me the solution in this example, and that's not true. The mathematics is similar. And what I want to do in this video is just to compare and to think about how proportions might be used, what the procedures are when we're using proportions to convert units, and the same thing with dimensional analysis, how they're different. So with proportions, it is a step-by-step procedure, meaning if we want to convert from one unit into another, if we don't have a direct conversion, let's say we're going from kilograms to ounces, and you don't have that direct conversion, you're going to have to do a series of intermediate problems. So you'll have to first convert into potentially pounds, and then from pounds into ounces. And it's a very step-by-step procedure. Comparing that to dimensional analysis is more fluid, meaning you still have to convert and have intermediate conversions, but you don't have to break it up into multiple problems. You can just add it as another step in the dimensional analysis procedure. With proportions, we use conversions factors as ratios. So the fact that there are 2.2 pounds in a kilogram, we're going to use that as a ratio and set that up within our proportion. So we're going to set that equal to some other ratio. In dimensional analysis, we use that more to cancel out pounds and go into kilograms, or kilograms and go into pounds. So it's still used essentially as a ratio, but we're using it in a context of multiplication. In a proportion, each step has an unknown x. There is a variable that you're going to see when you're using proportions. You're not going to have a variable with dimensional analysis. Instead, you're going to start with what you know, what you want to convert, and use multiplication and division until you get what you want. With proportions, you're going to start with a ratio and step by step use that ratio to find unknown quantities. And I think that'll make sense once we get into the problem here. And then finally, very generally, for proportions and ratios, the goal, this should say ratios, not radios, but we should use known ratios to solve for unknown quantities. So if you know that there are 2.2 pounds in 1 kilogram, you can use that to solve for, how many pounds does someone weigh if they weigh 12 kilograms. Okay, so something like that. Where dimensional analysis, the goal is specifically to convert units. And it may not seem obvious how these are different quite yet, but let's get into this example. So with a proportion, all right, if we're using proportions to simplify or solve this problem, I'm going to write down some ratios that I know I need to use. If you know the total number of grams and micrograms, so if you know the relationship between grams and micrograms, you would want to write that down. I don't. I mean, I do, but for this example, I'm going to pretend like I don't. But I do know a few ratios. I do know that 1 gram is made up of 1,000 milligrams. And I also know that 1 milligram is made up of 1,000 micrograms. So what I'm going to do is to use these facts. These are ratios that I know to be true. These are known relationships here. And I want to use them to solve and to convert or figure out what is 2.36 grams. So what I'm going to do first, I'm going to start with I'm going to change the 2.36 grams. I'm going to first convert that or find the unknown quantity in milligrams. And then once I know that in milligrams, I'm going to convert that into micrograms. And you're going to find that we're going to do the same thing with dimensional analysis. So first, I know that 1 gram is 1,000 milligrams. And I'm going to use a proportion. So a proportion, we're going to have equal ratios. So I know the relationship between milligrams and grams. I'm starting with 2.36. This should say 2.36 grams. I don't know how many micrograms. Notice in this example, my unknown is the number of, milligrams. I'm first converting to milligrams. That's the unknown. This is using an equal to. All right, I'm saying that the relationship between these two ratios, these are equivalent ratios. I'm going to solve this unknown for x by cross multiplying. 1x equals the product of 1,000 times 2.36. You're going to get x equal to 2,360. So 2.36 grams is equivalent to 2,360, in this case, milligrams. Okay, so that's helpful, but that's not quite the exact solution. I now need to convert this to micrograms. If you know a relationship between milligrams and micrograms, then we can use that known relationship to convert this, and we do, right? This known relationship is up here. I know 1 milligram is equivalent to 2,000, let me go back. 1 milligram is made up of 1,000 micrograms. I'm getting ahead of myself. I know that ratio to be true. But I don't have 1 milligram. I have 2,360 milligrams. I want to know what is that in micrograms. That is my unknown. So I set up my equivalent relationship here. These are equal ratios. I'm going to cross multiply. You'll get 1x equal the product. X will equal looks like we're going to get about 2,360,000. So we get 2,360,000, and this is micrograms. So we have converted our grams into micrograms, and maybe we can reflect back on what I have here. It's a step-by-step procedure, potentially. If you don't have a direct conversion, you might have to have an intermediate step, which I planned. It uses conversion factors as ratios. So I set up the 1 gram to 1,000 as an equivalent ratio of the quantity that I'm starting with and the unknown that I'm hoping to convert it to. Each step has an unknown. So when I first converted it to milligrams, I had an unknown x. When then I converted that milligrams to micrograms, I had an unknown x. And I used my known ratios, not radios, ratios to solve for unknown quantities. The unknown quantity here was the amount in milligrams. The unknown quantity here was the amount in micrograms. Now let's compare this to dimensional analysis. With dimensional analysis, you start with what you want to convert. Start with what you want to convert, or what you want to change. So in this case, I'm converting or changing the 2.36 grams, and I'm going to start with that over 1. I am still going to use my conversion factors. I'm still using 1,000 milligrams to 1 gram, and it doesn't matter if it's 1 gram over 1,000, but I know, maybe I'll write it this way. I know that 1 gram is equal to 1,000 milligrams, and I know that 1 milligram is equal to 1,000 micrograms. So I'm still using these known quantities, these known relationships here. But I'm specifically, and my goal here is to use multiplication. And I'm using these conversion factors within this dimensional analysis to cancel out units. So I want to cancel out grams, and I want to go first into milligrams. So I'm going to write that. Then I know when I am done with my milligrams, I want to cancel that out and go into micrograms. So I'm kind of mapping out my dimensional analysis before I start putting numbers places. I'm using multiplication here. Multiplication, not equal to. These are not equal to signs. And I'm not going to have any x's in here. These are all known values. Specifically, I know there's 1 gram in 1,000 milligrams, and 1 milligram is equivalent to 1,000 micrograms. So now there is no cross multiplying here. I multiply the numerators, 2.36 times 1,000 times 1,000. What I get is 2,360,000. And then I multiply the denominators. 1 times 1 times 1 is 1. And when you divide that, you get 2,360,000 micrograms. We get the same answer, the same quantity. And that's not, I mean, we should, right? This is not, just because one does things slightly different doesn't mean we should get different answers here. I hope you can see the difference between these two. Proportion, each step uses an unknown. We are relating these ratios here with an equal to sign, and we cross multiply to solve for that unknown. Dimensional analysis, there are no unknowns. There are no variables in here. I'm starting with what I want to convert, and I'm using my conversion factors to cancel out units. In this video, I will be going over how to convert 3,215 grams into ounces. And I'm going to use both proportion and dimensional analysis. Now, regardless of whatever method you use to make these conversions, my recommendation usually starts the same, and that is to map out what you're going to do. So the first question I need to ask myself is, do I have a direct conversion from grams into ounces? I don't. Off the top of my head, I don't know the number of grams relative to the number of ounces. I do know, though, if I have the number of pounds first, I could get the number of ounces. That's not too helpful right now because I don't know the number of grams into the number of pounds. But I do know grams to kilograms and kilograms to pounds. So I'm going to map this out. These are the conversion factor. These are the units that I will go into. First to kilograms, then to pounds, then to ounces. Now I'm going to start filling in, just very briefly, the conversion factors between these conversions. Between grams and kilograms, I know there are 1,000 grams in 1 gram, or 1 kilogram. I know that 1 kilogram is equal to 2.2 pounds, and I know that 1 pound is equal to 16 ounces. So I'm going to use these 3 facts here to go from grams to ounces. If I'm using proportions, you're going to use these conversion factors as ratios. So I'll start with the ratio. I'll start with one conversion factor that I know to be true, and that is 1 kg is equivalent to 1,000 grams. This is a ratio here. And I'm going to set that equal to an equivalent ratio of grams to kilograms. And in this problem, I know the number of grams. There are 3,215 grams. I want this number to me right now is an unknown in the unit of kilograms. So I want to convert that to kilograms. Remember, when we are using proportions, we have unknowns on each step, and we're going to be cross-multiplying to be solving for our unknown value of x. So I'm going to get 3.215, which is in a unit of kilograms. Okay, that's great. So now I know how many kilograms this individual weighs, this newborn. I want to now convert this to pounds. So I start with the conversion factor that I know. A little bit different than dimensional analysis. We're not starting with what we're trying to change necessarily. Let's start with a ratio or a factor here that we know to be true, something we know. We know the ratio. 1 kilogram is equivalent to 2.2 pounds. I'm going to set that equal to an equivalent ratio of kilograms to pounds, but specifically I'm looking for 3.215 kilograms. I don't know the number of pounds that this is. So I'll cross multiply. So all I need to do, if I multiply 2.2 times 3.215, find that product, I'm going to find the number of pounds. I got 7.073. So this number of kilograms, which we knew as an original number of grams, is equivalent to 7.073. Now, an important part of this particular problem is if you're using proportions and you know there's going to be multiple steps where you're solving for an unknown, as we're seeing here, you're not going to want to round your answer. If we rounded our answer at the beginning here at 3.2, this would have been a different number, right? 3.2 times 2.2 is 7.04, which you might not think is that big of a deal, but when we now go to the next number, every time we use that rounded number, our error is going to grow and grow and grow. So we want to just keep that number unrounded if possible. The final step here is to get to ounces. I know that 1 pound is equivalent to 16 ounces, so I'm going to set that up as a ratio, and I need that to be equal to some number of pounds. In this case, we know the number of pounds. We have the unknown number of ounces. So this is what I'm going to do. I'm going to cross multiply. 1x will equal the product of 16 and 7.073. And when you multiply 16 times 7.073, you get 113.168. So let me erase that slightly. 168. Now I'm going to round this to the tenths place. So we'll say that this individual weighs approximately 113.2 ounces. So again, just to summarize here, what we have using proportions is I still mapped out what I was going to do, going from grams to kilograms to pounds to ounces, and I'm considering the factors here, the factors that I'm going to use to convert, the equivalent relationships, and I use them as a series of ratios. And not only as a series of ratios, but I'm thinking about them as a ratio equivalent to some other ratio of grams to kilograms, or kilograms to pounds, or pounds to ounces, where the unknown, the x, is what I'm trying to convert to in that step, right? What do I want to convert this to? That's what the unknown is. You notice that there are multiple steps that we have to do. Now, dimensional analysis is going to be slightly different. Dimensional analysis is still going to use these 100 or 1,000 grams equal to 1 kilogram, so I'm still going to write these down. 1 kilogram is going to be equivalent to 2.2 pounds. And 1 pound is going to be equivalent to 16 ounces. We're still using these, and my plan is still to go from grams to kilograms to pounds to ounces. That's still the plan. But instead of starting and first, going from, starting with our conversion factor, dimensional analysis, once again, is used to change units. Change what units? Well, the 3,215 grams, that's the unit we want to change, the unit of grams, because this is not the unit we want. We want to cancel this unit. How do we cancel this? We're going to cancel this with a series of multiplication and division, using our conversion factors, dividing out by that unit that we don't want, and multiplying by its equivalent value in its new unit. So, when I am going through here, I'm going to be multiplying at each step. So I'm going to multiply by some conversion factor, specifically the one where I'll cancel out grams and go into kilograms. Now I'm just going to go ahead here and just write out all of the conversion factors. I might as well. So I'm just going to set up my dimensional analysis. Once I multiply by grams into kilograms, I'll have my grams converted to kilograms, but then I want to convert kilograms into pounds. Kilograms, my next conversion factor will be in the denominator because I want to cancel out the numerator. And then my answer will be in pounds, but I want to cancel that and go into ounces. So all I'm doing here is setting up my dimensional analysis with my units, and now I'm ready to go back and put in the correct values so that these are set up properly. I know that 1 kilogram is 1,000 grams. I know there are 2.2 pounds in 1 kilogram and 16 ounces in 1 pound. Now, if you have, and I see students do this, I see students starting to write X's or unknowns in the dimensional analysis. I see them write equal to signs here. That is not correct. They tend to mold these two ideas of proportions and dimensional analysis into something that's not true. We start with what we want to change. and we want to cancel that unit, so the next factor that we multiply by needs to have that unit in the denominator, and we're converting it to a unit, whatever's in the numerator. And we're using multiplication, so these multiplication values here, these multiplication symbols need to be in there. So when you're multiplying these, another mistake, students start to cross multiply. Again, confusing it with proportions. But all we're doing here is multiplying these fractions, multiplying these rational numbers. So I'm going to be multiplying all the numerators. So when you put that in your calculator, when you take 3,215 times 2.2 times 16, you should get 113,168. Oops, let me change to the pen. And when you multiply 1 times 1,000, 1, you get 1,000. And when you simplify that, you're going to get 113.168, which again, we're going to round to the tenths place, about 113.2. And the unit here is our last one that we converted to, which was ounces. And we have no unit in the denominator, right? There's no unit in the denominator. Notice both processes here gave us the same value as it should. I'm hoping with these two examples in this video you can see the differences between when we use, or when we would use, proportions versus dimensional analysis. Students tend to like dimensional analysis for these examples because it's a lot quicker. You don't have to stop after each step to find our unknown value. We just go through. Now, some people like to use proportions because that's the way that they think about these relationships. Either one is appropriate, and either one would be acceptable on an exam.